If you're a string theorist, then maybe you're done. We have described the calculations and all of the answers, and we know everything. But if you're interested in astronomy and have some interest in the real world, then now we'll discuss some of how we know about all these things and all the great phenomena that have taught us, and some more about the consequences. So, one of the most exciting discoveries in this field is the discovery of ancient light, essentially the farthest thing we can see. Where does this come from? Well, remember there was this time of ionization when the temperature was about 3000 Kelvin, and that means that the radiation gas had an average energy corresponding to kb times 3000 Kelvin. That's exactly the ionization energy for ionizing a hydrogen atom. At temperatures above that, hydrogen atoms were unstable because the ambient photons in the photon gas could just knock electrons out of hydrogens, so there were no hydrogen atoms. There was a dense plasma, and at later times, as the universe cooled, hydrogen formed atoms, and we had neutral hydrogen atoms by and large, though they were later reionized in, as I said, in the hot intercluster gas clouds. But after recombination, radiation essentially decouples from matter. So photons that existed at the ambient temperature, at the ambient energy, these were ultraviolet photons with a temperature corresponding to a temperature blackbody spectrum with a temperature of 3000 Kelvin. That light spectrum, as once neutral hydrogen atoms formed, those photons basically proceeded through the universe unimpeded. Some of them, of course, bumped into little fluctuations like stars and galaxies. Since most of space is empty, most of those photons are still around. And the energy in that radiation field has been conserved. Those photons are still here, except they've been redshifted. And so we can compute, since this happened at Z of about 1100, the temperature will have decreased by the scale growth of the scale factor by a factor of 1000. We expect the universe to be imbued, to be bathed in a blackbody, in a gas of blackbody photons with a temperature of about 3 degrees Kelvin. And this was realized by a theorist at Princeton named Dicke in 1960, and this had been predicted by several other works that we'll turn to later. But Dicke in 1960 has the idea that he's a radio astronomer and he can build a Dicke radiometer and try to measure this. And indeed, he set some of the researchers in his group to try to design a Dicke radiometer to measure this relic radiation from the Big Bang, if you want direct evidence for the Big Bang. Now, independent of that, 30 miles from Princeton at AT&T Bell Labs, two engineers, Penzias and Wilson, are building a Dicke radiometer. Their idea is they're trying to develop the technology that would become satellite communication. So they build this great big huge horn radio antenna that's here seen on the right. And there's a noise. As always happens with experimenters, with experiments, the experiment is not perfect and their antenna picks up some noise. And they try to clean the contacts, and they have this humorous episode where a family of pigeons had made their home in the antenna. Look at the size of the thing, and they spend a few quality days scraping pigeon droppings from the antenna, thinking maybe this is the cause of the noise. Nothing removes the noise. Usually when that happens in a radio experiment, you are probably receiving the BBC from somewhere. So they turn their antenna in different directions. It's a very directional antenna, and they find that the noise is the same from every direction. They rule out all terrestrial sources. They try to imagine maybe this is from some astronomical source, so they try to check whether when they aim it at the plane of the galaxy or away from the plane of the galaxy, they get a different signal. The signal doesn't care where they're aiming it. The signal is completely isotropic. It's not terrestrial. It's not galactic. In despair, they call an eminent theorist. Luckily, they call Dicke at Princeton, and at least legend has it that he is interrupted in the middle of a group meeting by a call from these engineers at AT&T Bell Labs who want to ask a question, and Dicke comes back. I think it was just Bell Labs back then. Dicke comes back and tells the research group, don't worry about designing that radiometer. We've been scooped. What these guys had discovered was indeed the 3-degree thermal radiation at microwave wavelengths that is the relic remnant of the 3000 degree photons that were around when hydrogen atoms first formed, and since then we've learned a lot about this background radiation. In particular, it is a black body. Remember that a redshifted black body remains black body spectrum, except the temperature has decreased. And what you see here is experimental measurements from the COBE satellite in the 90s and fit to a black body spectrum. And this is as beautiful a fit as you can get. So we have measured the temperature of the universe, and the temperature of at least the photon gas in the universe. Matter, of course, is at essentially zero temperature. Dust is cooled down to zero, but the temperature of the radiation field in the universe is about 2.726 Kelvin, and we know this with high precision. And this, the other important point, other than it's a black body spectrum, validating the fact that this comes from some primordial, hot, dense universe, is that it's isotropic to a degree of 1 part in 100,000. So this, if you want, is a great validation of our cosmological principle that the universe is homogeneous and isotropic, because the black body radiation that it fills the universe is the same in all directions. For this discovery, of course, Penzias and Wilson received the Nobel Prize in 1978. Notice that this is the answer to the question, how far can you see? This is the oldest light you can ever see. Why is this the oldest light? This is the universe as it was when it was 380,000 years old. Of course, there was 380,000 years of history before that, but we'll never see them because photons created then interacted strongly with the plasma, were absorbed and re-emitted and absorbed and re-emitted. And then eventually the photons that were emitted 380,000 years ago, those are the photons that are still around. So this is the most distant and the most far into the past that we can ever see. We'll never, for example, see the Big Bang. So this is a very good image. This describes the temperature fluctuation of the microwave background. The microwave background is extremely isotropic. If you were wanting some evidence for isotropy of the universe, this is about as good as it gets. But when in the 90s COBE makes more precise measurements of the precise blackbody spectrum, you find that there is temperature variation. The temperature is not completely uniform. This is, in fact, the same map with higher precision, blue representing regions that are slightly hotter, red representing regions that are slightly colder. Obviously, this was done by astronomers. And you see that there's a blue region in the sky and diametrically opposed, 180 degrees away, a red region in the sky. The black body spectrum of the universe is not isotropic. I know what that means. That means that we are not at rest relative to the Hubble flow. This is a measurement of the Earth's motion relative to the local Hubble flow. This is our peculiar motion. What we are seeing is that we are moving in a particular direction. In fact, subtracting Earth's motion around the Sun and Sun's motion around the Milky Way, all of which have an effect, you see that what we have really measured is that our local cluster as a whole is moving with a peculiar velocity of 600 kilometers per second in the direction of the Virgo cluster. And again, that's not exactly our motion because you have to subtract all kinds of motion around the Milky Way to get that. But that we know, when we subtract that, we find 600 kilometers per second towards Virgo as the motion of the local cluster. So there is a local rest frame. It's determined by the cosmic microwave background, and we can measure our velocity relative to that. And the universe is really, really, really very isotropic.